Summer, 1938. Hamburg, Germany. Colonel Nikolaus Ritter of the Abwehr leaned forward across his desk as Hermann Lang sketched another component from memory, his pencil moving with the precision of a man who had assembled these mechanisms hundreds of times. "This is the stabilization platform," Lang explained, his voice steady despite the significance of what he was revealing. "The gyroscopes maintain a level reference point regardless of aircraft attitude. It connects here to the sighting head through a coupling mechanism." Ritter watched in silence, calculating the implications. Before him, reconstructed entirely from the memory of a German-born inspector who worked at the Carl L. Norden Company in New York, lay the complete design of America's most closely guarded bombing technology. The device Lang described promised to revolutionize high-altitude precision bombing, turning strategic air warfare from a blunt instrument into a surgical tool. What neither man yet understood was that this intelligence windfall, obtained at considerable risk and expense, would ultimately prove irrelevant to Germany's war. The Luftwaffe would examine these plans, build test units, compare them against their own designs, and reach a conclusion that would fundamentally misunderstand the nature of the technological war to come. They would decide that America's miracle weapon was unnecessarily complex, operationally impractical, and strategically misguided. By the time German engineers understood what American precision bombing had actually achieved, it would be far too late to matter. The story of this technological divergence began not with espionage but with doctrine, shaped years before the first bomb fell. In the aftermath of the Great War, military theorists across the developed world grappled with the implications of air power. British theorist Hugh Trenchard had articulated the concept of strategic bombing, the idea that aircraft could bypass ground armies entirely and attack an enemy's industrial capacity and civilian morale directly. American air power advocates, led by Brigadier General Billy Mitchell, had demonstrated the potential in spectacular fashion. In July 1921, Mitchell's airmen had sunk the captured German battleship Ostfriesland off the Virginia coast using aerial bombs. It had taken 65 bombs to accomplish the task against a stationary target that could not maneuver or return fire, but the principle had been proven. Aircraft could potentially destroy capital ships, threatening naval supremacy itself. The demonstration impressed many, but it also revealed a fundamental problem. High-altitude bombing was extraordinarily inaccurate. Bombs dropped from altitude were subject to wind drift, variations in air density, the aircraft's speed and heading, and the ballistic characteristics of the munition itself. Without a way to calculate these variables and adjust aim accordingly, bombers would need to drop hundreds or thousands of bombs to ensure hits on point targets. The inefficiency was staggering. Strategic bombing would require not precision but saturation, the deliberate destruction of entire areas to ensure that military targets within those areas were hit. This approach troubled American military planners for reasons both practical and philosophical. The United States Army Air Corps, struggling for independence from Army control and legitimacy as a decisive military arm, needed to demonstrate that air power could achieve strategic objectives without resorting to the mass destruction of civilian areas. Precision bombing offered a moral justification for strategic air warfare. If bombers could strike factories, rail yards, power plants, and military installations with minimal collateral damage, then strategic bombing could be presented as humane warfare, destroying an enemy's capacity to fight while minimizing civilian casualties. The problem was technological. Existing bombsights of the early 1920s worked on vector calculation principles. The bombardier would estimate the wind speed and direction, calculate the aircraft's ground speed, determine the appropriate lead angle, and mark a release point. The entire process was manual, time-consuming, and prone to error. Any change in conditions during the bombing run, any gust of wind or variation in airspeed, would throw off the calculations. The accuracy that precision bombing required simply did not exist. The United States Navy's Bureau of Ordnance recognized this limitation and sought to overcome it through technological development. In January 1920, they contracted with an engineer named Carl Lucas Norden to develop an improved bombsight. Norden had been born in Semarang, Java, in April 1880, the son of Dutch parents. After his father's death in 1885, the family had returned to the Netherlands, and young Karl had eventually studied mechanical engineering at the Federal Polytechnic Institute in Zurich, Switzerland. He had immigrated to the United States in 1904, working first for various machinery companies before joining Elmer Sperry's firm in 1911. At Sperry Gyroscope Company, Norden had worked on gyrostabilization systems for naval vessels, devices that used spinning gyroscopes to maintain stable platforms despite a ship's rolling and pitching motion. The work required meticulous engineering and an understanding of complex mechanical systems. Norden proved exceptionally skilled at both, but his relationship with Elmer Sperry was tempestuous. Both men were perfectionists with strong opinions and difficult personalities. Sperry reportedly disliked Norden's habit of smoking vile black cigars, while Norden resented Sperry's insistence that he sign over future patent rights to the company. They parted ways in 1913, with Norden establishing himself as an independent consulting engineer. During the First World War, Norden had worked on various military projects, maintaining connections with the Navy's Bureau of Ordnance. When the Bureau approached him in 1920 about developing an improved bombsight, he understood immediately that the problem was fundamentally one of stabilization and computation. The bombardier needed a stable platform from which to sight the target, unaffected by the aircraft's pitch, roll, and yaw. He needed a means of continuously calculating the bomb's trajectory based on changing flight conditions. And he needed a way to maintain aim on the target despite the aircraft's forward motion, keeping the crosshairs centered while the bomber flew at speeds exceeding 200 miles per hour. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Norden approached the problem methodically, drawing on his experience with gyrostabilizers and mechanical computing systems. His initial designs combined a gyroscopically stabilized platform with telescopic sighting optics and mechanical calculators that could solve bombing equations continuously during the approach to the target. The first prototype, designated the Mark 11, was completed in 1927. It was a complex device, weighing approximately 50 pounds and containing hundreds of precisely machined parts. The bombsight consisted of two primary assemblies. On the left side sat the stabilization platform, a gyroscope-mounted system that maintained a level reference regardless of the aircraft's attitude. This platform kept the optical sighting system pointed toward the ground, even as the bomber pitched and rolled through turbulent air. On the right side was the sighting head, containing the telescope through which the bombardier viewed the target, along with the mechanical analog computer that calculated the bomb release point. The analog computer represented remarkable engineering for the era. Using a series of gears, cams, and integrators based on the ball and disc mechanism borrowed from differential analyzer technology, it could continuously solve the complex differential equations that described the bomb's trajectory. The bombardier would input the aircraft's altitude, the bomb's ballistic characteristics, and the initial airspeed and heading. From that point, the computer would track the aircraft's actual ground speed by measuring the rate at which the target moved through the sighting telescope. This direct measurement of ground speed eliminated much of the guesswork inherent in earlier bombsights. If the wind was stronger than estimated, pushing the aircraft faster across the ground, the computer would detect this through the increased rate of target motion and adjust the release point accordingly. The sighting process worked through a clever optical arrangement. The bombardier would locate the target through the telescope and bring it under the crosshairs. He would then engage the computer, which would begin tracking the target's motion. As the bomber approached, the target would appear to move backward in the field of view as the aircraft overtook it. The computer would continuously adjust the crosshairs' position, moving them ahead of the target to compensate for the bomb's fall time. When the moving crosshairs and the fixed target image coincided, the bomb should be released. Initial testing of the Mark 11 showed promise, but revealed significant limitations. The device required extensive setup time before each bombing run. The gyroscopes needed to be leveled precisely, a process that could take 10 minutes or more. The bombardier had to manually adjust multiple controls during the approach, dividing his attention between sighting through the telescope and manipulating the mechanical inputs. Most critically, the bombsight could not compensate for crosswind drift. If the wind was pushing the aircraft sideways relative to its heading, the bombardier had to manually adjust the drift angle, a procedure that required skill and introduced opportunities for error. Norden continued refining the design throughout the late 1920s and early 1930s. In 1928, he partnered with Theodore Harold Barth, a former Army colonel who had worked in chemical warfare development during the Great War. Barth handled the business aspects of their venture, forming Carl L. Norden Incorporated, while Norden focused on engineering. Their collaboration produced the Mark 15 in 1931, a substantially improved design that addressed many of the earlier model's limitations. The Mark 15 incorporated automatic stabilization that reduced setup time, improved the optical system for better target visibility, and most significantly, developed a more sophisticated computer that could handle drift calculations automatically. Navy testing in October 1931 pitted the production Mark 11 against the prototype Mark 15. The results were striking. The Mark 11 achieved 23% direct hits against test targets. The Mark 15 achieved 50% direct hits under the same conditions. The United States Army Air Corps, observing these tests, immediately recognized the Mark 15's potential and negotiated to acquire the design for their own use. The bombsight that emerged from this development program was a masterpiece of pre-war mechanical engineering. The production model weighed approximately 50 pounds and contained over 2,000 individual parts, each machined to tolerances measured in thousandths of an inch. Skilled craftsmen, many of them German and Italian immigrants working in Norden's New York factory, hand-assembled each unit. The manufacturing process was labor-intensive and slow. Between 1932 and 1938, the Norden Company produced only 121 bombsights per year. Each device cost approximately $10,000 to manufacture in 1930s currency, an extraordinary sum for a single piece of equipment. The technical specifications were impressive by the standards of the era. In peacetime testing, under ideal conditions, clear weather, no enemy action, experienced bombardiers, the Norden demonstrated a circular error probable of 75 feet from altitudes of 20,000 feet. This meant that half of all bombs dropped would fall within a 75-foot radius of the aim point. For comparison, a typical factory building might measure 300 feet on a side. In theory, the Norden could place bombs directly onto specific structures, from altitudes where anti-aircraft fire was relatively ineffective and fighter interception difficult. The performance seemed to validate the precision bombing doctrine that American air power advocates had been developing. If bombers could hit individual buildings from 4 miles up, then strategic air warfare need not involve the wholesale destruction of cities. Factories could be destroyed while leaving surrounding residential areas intact. Rail yards could be cratered without leveling adjacent neighborhoods. The United States could wage strategic air warfare while maintaining moral high ground over adversaries who practiced area bombing. This optimistic assessment overlooked significant practical limitations that would become apparent only in combat. The 75-foot accuracy required nearly perfect conditions. The bombardier needed clear visibility of the target from initial acquisition through bomb release. The atmospheric conditions along the bomb's entire fall needed to be precisely known or accurately estimated. The aircraft needed to maintain a stable heading and altitude during the final approach, typically lasting a minute or more. Any defensive maneuvering, any evasive action to avoid flak or fighters, would disrupt the bombing run and invalidate the computed solution. The Norden also required extensive training to operate effectively. Bombardiers attended specialized schools, where they learned the device's complex operational procedures. They practiced on bombing ranges, dropping practice bombs on targets painted on desert floors, refining their technique under conditions far removed from combat stresses. The training took months and cost the Army Air Forces thousands of dollars per bombardier. By the late 1930s, the Norden had become America's primary technological answer to the precision bombing challenge. The device was so highly regarded that security around it became extraordinarily tight. Bombardiers were required to swear an oath protecting the bombsight's secrets. They were instructed to destroy the device if capture seemed imminent, either by shooting it with their sidearm or by igniting a thermite grenade installed in the aircraft for that specific purpose. When not in use, Norden bombsights were stored in guarded vaults. Armed sentries accompanied the devices whenever they were transported from storage to aircraft. The elaborate security procedures reflected both the bombsight's genuine technological sophistication and the investment in promoting precision bombing as America's distinctive contribution to strategic air warfare. This wall of secrecy, however impressive its appearance, was already compromised by the time Hermann Lang walked into Colonel Ritter's Hamburg office in the summer of 1938. Lang had been born in Germany in 1901 and had immigrated to the United States in 1927 at age 26. He had taken employment at the Carl L. Norden Company's factory on Lafayette Street in Lower Manhattan, working as an inspector and draftsman. His position gave him access to the bombsight's complete technical drawings and assembly procedures. He apparently considered himself a German patriot despite his American citizenship, and he viewed providing the bombsight's secrets to Germany as a duty to his homeland. The Abwehr had recruited him as part of what would later be known as the Duquesne spy ring, a network of German intelligence agents operating in the United States under the direction of Fritz Joubert Duquesne, a South African with deep hatred of Britain who had spied for Germany during both world wars. Lang's value to the Abwehr was extraordinary. Rather than risking the theft of physical drawings that might be noticed, he memorized the bombsight's design through repeated study of the plans he accessed as part of his legitimate work. Over months, he committed to memory the dimensions, specifications, and assembly procedures for hundreds of components. In the summer of 1938, he traveled to Germany on what appeared to be a vacation, meeting with Colonel Ritter and other Luftwaffe technical experts in Hamburg. There, over several days, he reconstructed the complete design from memory, sketching components and describing assembly procedures in detail, sufficient for German engineers to build working copies. For this intelligence coup, Lang received 10,000 Reichsmarks, equivalent to roughly $3,000 American at contemporary exchange rates, along with the Abwehr's gratitude for providing what they believed was America's most valuable military secret. Ritter forwarded Lang's reconstructed plans to Luftwaffe Technical Services with a recommendation for immediate exploitation. The German Air Ministry directed the Telefunken electronics firm and the Carl Zeiss Optical Company to examine the American design and compare it against Germany's own bombsight development programs. What happened next would shape the divergent paths of American and German strategic bombing doctrine for the remainder of the war. German engineers did indeed build mock-ups of the Norden bombsight based on Lang's information. They studied its principles, analyzed its strengths, and identified its weaknesses. Then they made a decision that would prove strategically catastrophic. They concluded that the Norden, while technically impressive, was unnecessarily complex for Germany's needs. The Luftwaffe's bomber doctrine emphasized tactical air support for ground forces and medium-altitude precision attacks using dive bombing techniques. The Norden was optimized for high-altitude level bombing, a mission profile Germany had deliberately chosen not to pursue. Its complexity made it difficult to manufacture in quantity and challenging to maintain under field conditions. The Germans had been developing their own bombsight, the Carl Zeiss Luftfernrohr 7, commonly abbreviated Lotfe 7. This device employed similar principles to the Norden, using gyroscopic stabilization and analog computation, but it was significantly simpler in execution. The Lotfe 7 combined the stabilization platform and optical system into a single compact unit, rather than separating them as the Norden did. It used fewer components, required less maintenance, and was easier to operate. Most importantly for German needs, it worked effectively at the medium altitudes where Luftwaffe bombers typically operated. German technical assessments of the Norden acknowledged its sophistication, but concluded it offered no significant advantages over the Lotfe 7 for Germany's operational requirements. The decision was made to continue with German development rather than attempting to copy the American design. Hermann Lang returned to the United States and continued feeding information to the Duquesne spy ring, unaware that his greatest coup had been filed away as interesting but non-actionable intelligence. The Federal Bureau of Investigation had been tracking the Duquesne network for years, using wiretaps and surveillance to map its membership and activities. In June 1941, 6 months before Pearl Harbor brought America into the war, the FBI arrested 33 members of the spy ring in coordinated raids across New York. Lang was among those apprehended. At trial, prosecutors presented evidence that Lang had provided bombsight secrets to Germany and had continued supplying military intelligence through 1941. He was convicted of espionage and sentenced to 18 years in federal prison. The trial received significant press coverage, with newspapers breathlessly reporting that America's most guarded military secret had been compromised years before the war began. What the American public did not know, and what would not become clear until post-war interrogations of Luftwaffe personnel, was that the compromise had ultimately made little strategic difference. Germany had obtained complete knowledge of the Norden's design and had chosen not to exploit it. The decision reflected fundamentally different conceptions of strategic bombing between American and German air forces. The United States Army Air Forces built their entire strategic bombing doctrine around precision high-altitude attacks on specific industrial and transportation targets. This approach required sophisticated bomb sites, like the Norden, heavy bombers capable of carrying significant bomb loads to high altitude, and long-range fighter escorts to protect the bombers during daylight operations. The doctrine accepted high costs in aircraft and trained crews as the price of destroying Germany's industrial capacity while minimizing deliberate attacks on civilian areas. Germany's Luftwaffe had developed along different lines, shaped by different strategic circumstances and doctrinal priorities. German air doctrine emphasized close support for ground forces, the use of bombers as flying artillery to blast paths for advancing armies. This mission required aircraft that could operate at lower altitudes, delivering ordnance with precision through dive bombing techniques or medium-altitude level bombing. The Junkers Ju-87 Stuka, the Luftwaffe's iconic dive bomber, epitomized this approach. With screaming sirens and near-vertical attack profiles, Stukas could place bombs with remarkable accuracy on point targets, but they were vulnerable at low altitude and had limited range and payload capacity. For longer-range strikes, Germany employed medium bombers like the Heinkel He-111 and Junkers Ju-88. These aircraft operated at altitudes where the simpler Luftwaffe 7 bombsight worked adequately. They did not need the Norden's complexity because they were not being asked to bomb from 20,000 feet in formation through heavy flak and fighter opposition. This doctrinal difference had roots in Germany's strategic situation and recent combat experience. The Luftwaffe had been bloodied during the Battle of Britain in 1940, losing hundreds of bombers to RAF fighters when attempting daylight raids on British cities and industrial targets. The experience had convinced Luftwaffe commanders that unescorted bombers, regardless of their altitude capability, could not survive against determined fighter opposition during daylight hours. Germany had shifted to night bombing, trading accuracy for survival. British cities had burned under night raids, but precision attacks on specific factories or rail yards proved nearly impossible in darkness, despite the Luftwaffe 7's capabilities. By 1943, when American heavy bombers began appearing over German-occupied Europe in large numbers, the Luftwaffe had largely abandoned strategic bombing in favor of air defense and tactical support missions. The massive four-engine bombers Germany had designed before the war, the Heinkel He-177 and Junkers Ju-390, never reached operational effectiveness in significant numbers. Resources were diverted to fighter production to counter the growing Allied bomber offensive and to V-weapons. The vengeance weapons, like the V-1 flying bomb and V-2 rocket, that Hitler believed would break British morale through terror rather than precision. The collision between American bombing doctrine and combat reality began in earnest on March 18, 1943, when the 303rd Bombardment Group attacked the Wegesach shipyard near Bremen, Germany. This mission marked the first large-scale operational use of the Norden bombsight over German territory under the conditions for which it had been designed. The results appeared promising. The 303rd managed to put 76% of their bombs within a 1,000-foot radius of the aim point, demonstrating accuracy well beyond what earlier bombing missions had achieved. The performance seemed to validate years of development and the extraordinary security measures surrounding the device. But this mission represented ideal conditions that would prove impossible to replicate consistently. The weather had been clear, providing excellent visibility. German fighter opposition that day had been lighter than usual. The flak, while heavy, had not forced the formation to take evasive action during the critical final minute of the bombing run. Most importantly, the bombardiers flying that mission represented the 8th Air Force's most experienced crews, men who had completed multiple training sorties and understood the Norden's complex operational procedures intimately. As the strategic bombing campaign intensified throughout 1943 and into 1944, the gap between the Norden's theoretical capabilities and its actual combat performance became undeniable. Statistical analysis of bombing missions revealed troubling patterns. The average circular error probable in 1943 was 1,200 feet, not the 75 feet achieved in peacetime testing. Only 16% of bombs fell within 1,000 feet of the aim point. A standard 500-pound bomb, the workhorse of precision bombing missions after 1943, had a lethal radius of only 60 to 90 feet. At the actual combat accuracy being achieved, dozens or hundreds of bombs would be required to ensure destruction of a point target. Combat conditions bore little resemblance to the controlled environment of testing ranges. Over Germany, bombardiers faced intense anti-aircraft fire that forced pilots to take evasive action during bombing runs, disrupting the stable heading and altitude the Norden required. German fighters attacked formations before and during bomb runs, forcing defensive maneuvers. The weather over Central Europe, particularly in winter, produced overcast conditions that obscured targets or allowed only brief glimpses through cloud breaks. Industrial haze from factory districts made target identification difficult, even on relatively clear days. The stress of combat itself affected performance. Bombardiers crouched in unheated plexiglass noses at altitudes where temperatures reached 40 degrees below zero, breathing pure oxygen through masks, wearing heated suits and gloves to prevent frostbite, all while managing the Norden's complex controls under conditions where one mistake, one deviation from procedure, could send bombs into civilian neighborhoods rather than military targets. The device's mechanical complexity introduced additional failure modes that had not been apparent during peacetime operation. Vibration from the aircraft's engines and from nearby flak explosions could knock the gyroscopes out of alignment. Electrical surges disrupted the motors that drove the computing mechanisms. Carbon dust from the motor brushes contaminated sensitive bearings, introducing friction that degraded computational accuracy. Cold temperatures caused lubricating oils to congeal, slowing the mechanical calculator's operation. By late 1944, as many as 75% of some batches of Norden bombsights were failing to meet specification, missing targets by 280 feet from 20,000 feet altitude, when specifications called for 50-foot accuracy. Maintenance personnel struggled to keep the devices operational. Each bombsight required careful calibration before every mission. The stabilization platform's gyroscopes drifted over time and needed to be re-leveled, a procedure requiring comparison against precision spirit levels viewed through the stabilizer's inspection window. The analog computer's mechanical components wore with use, introducing backlash into gear trains that affected accuracy. Optical components fogged or frosted in the extreme cold, requiring heated blankets to be wrapped around bomb sites before missions. The security restrictions that had made sense in peacetime became operational hindrances in war. The requirement that bomb sites be stored in vaults and escorted by armed guards complicated pre-flight preparations. Bombardiers could not work on their devices between missions to familiarize themselves with individual quirks. Maintenance techs faced restrictions on accessing the devices for routine service. The elaborate security apparatus consumed resources that might have been better applied to training or equipment improvement. American bomber commanders confronted an uncomfortable reality by mid-1944. Precision bombing, as doctrine had envisioned it, was not achieving its objectives. Individual factories targeted for destruction often resumed production within weeks of raids that had cost dozens of bombers and hundreds of trained airmen. Malcolm Gladwell would later analyze a 22-mission campaign against a German chemical factory in 1944, revealing that only 10% of 85,000 bombs dropped actually hit the target area. Of those hits, only 40% of the munitions detonated. The factory, despite receiving concentrated attention from experienced bomber groups, was back in operation within weeks of the final raid. When Lieutenant General James Doolittle assumed command of the 8th Air Force in January 1944, he confronted these statistics and made a doctrinal shift. Precision bombing attempts against specific buildings or structures were largely abandoned. The 8th Air Force adopted tactics similar to RAF Bomber Command, conducting area raids with 750 to 1,000 bombers against large target complexes. Rather than attempting to hit individual factories, entire industrial districts became the aim point. The lead bomber in each formation would signal bomb release, and the entire formation would drop on that signal, carpeting an area measured in square miles with high explosives and incendiaries. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. This shift to area bombing paradoxically improved accuracy statistics. By late 1945, the 8th Air Force was placing 60% of bombs within 1,000 feet of aim points, achieving a circular error probable of approximately 900 feet. This improvement came not from better bomb sights or more skilled bombardiers, but from changed definitions of success. The aim point was no longer a specific building, but a geographic coordinate within a target area. Bombs falling anywhere within that area were counted as hits, even if they struck residential neighborhoods rather than military installations. The strategic bombing campaign's effectiveness remains debated among historians. The United States Strategic Bombing Survey, conducted immediately after the war, concluded that strategic bombing had significantly disrupted German war production and hastened Germany's defeat. Later analysis suggested that Germany's lack of natural resources and manpower shortages played larger roles in German industrial decline than bomb damage. German armaments production actually increased through 1944 despite intensive bombing, reaching peak output in autumn of that year, before finally collapsing in 1945, when transportation networks were systematically destroyed and raw materials could no longer reach factories. What became clear in post-war analysis was that the Norden Bombsight had not delivered the transformation in strategic air warfare that pre-war doctrine had promised. The device worked superbly under ideal conditions, but those conditions rarely existed in combat. Its complexity made it difficult to manufacture, maintain, and operate under stress. Its requirement for stable, uninterrupted bombing runs made it vulnerable to enemy countermeasures. Most fundamentally, the precision bombing doctrine built around the Norden had underestimated the resilience of industrial targets and overestimated the ability to identify and strike crucial nodes in an enemy's production network. The irony of Hermann Lang's espionage operation became apparent only after the war, when Allied interrogators questioned captured Luftwaffe technical personnel. The Germans confirmed that they had received complete details of the Norden bombsight in 1938, that they had built test units and evaluated the design thoroughly, and that they had concluded it offered no advantages for Germany's operational needs. While American security services had frantically protected the Norden's secrets, classifying it at levels rivaling the Manhattan Project's atomic bomb program, Germany had possessed those secrets all along and had deliberately chosen not to exploit them. This decision reflected the fundamental difference in how American and German air forces conceived strategic bombing. The Americans committed to high-altitude precision attacks because they believed they could achieve decisive strategic effects while maintaining moral distinction from the enemy's terror bombing campaigns. They invested over $1 billion in Norden bombsight production, equivalent to 2/3 of the Manhattan Project's cost. They built a massive training infrastructure to teach 50,000 bombardiers how to operate the complex device. They accepted horrific casualties among bomber crews, with loss rates sometimes exceeding 10% per mission, because they believed precision bombing would end the war faster and with less total suffering than alternative strategies. Germany, shaped by different strategic circumstances and doctrinal traditions, had pursued tactical air power and close support missions that did not require sophisticated high-altitude bomb sites. The Luftwaffe's focus on supporting ground operations made sense given Germany's continental position and the likelihood that German forces would fight primarily on land against the Soviet Union and Western allies. But this focus came at the cost of long-range strategic capability that might have proven decisive in other circumstances. The question of what might have happened had Germany invested heavily in four-engine heavy bombers, and precision bombing doctrine remains counterfactual speculation. Germany's industrial capacity was smaller than America's and Britain's combined. Its access to strategic raw materials was limited. The decision to focus on tactical air power, rather than strategic bombing, may have been inevitable given these constraints, regardless of bombsight technology. But the choice was made easier by German engineers' assessment that the Norden represented unnecessary complexity for missions the Luftwaffe was actually flying. When German officials examined the American bombsight in the late 1930s, they were seeing a solution to a problem they had decided not to solve. The American fascination with precision, high-altitude bombing seemed, from German perspective, to miss the point of air power's role in combined arms warfare. History would prove German doctrine inadequate for the strategic air war that actually developed, but that judgment came only in hindsight, after Germany had committed to a different path. The combat effectiveness of the Norden bombsight must be evaluated against the alternatives available. British bombing doctrine, after suffering unsustainable losses in daylight raids during 1940 and 1941, had shifted to night area bombing using simpler bombsights like the Mark 14. British circular error probable in night raids typically exceeded half a mile. Entire cities became targets because specific factories could not be identified in darkness. RAF Bomber Command accepted that precision was impossible under their operational conditions and opted for maximum destructive effect across wide areas. The American commitment to daylight precision bombing, enabled by the Norden and protected by long-range fighter escorts, represented a genuine attempt to achieve military objectives while minimizing deliberate attacks on civilian populations. That this attempt fell short of its goals does not diminish the moral and strategic logic behind the effort. The Luftwaffe 7 that Germany chose over the Norden represented a different set of compromises. The Luftwaffe 7 was simpler, cheaper to produce, easier to maintain, and adequate for medium-altitude level bombing. It consisted of a single metal housing containing the majority of the mechanism, with a mirror tube extending through the aircraft's fuselage to provide the bombardier a forward view. The mirrors that reflected the target image eliminated the Norden's restriction to nearly vertical views, allowing the Luftwaffe 7 to sight targets from 90 degrees forward to 40 degrees ahead of the aircraft. This flexibility simplified bombing procedures, as bombardiers could acquire targets earlier and had more time to refine their aim. The Luftwaffe 7's automatic bombing release triggered when the sight's computed release point matched the actual sighting point, reduced timing errors that human operators might introduce. The device's 3 large knobs for aim adjustment were simpler to manipulate than the Norden's multiple smaller controls. German bombardiers could operate the Luftwaffe 7 with less training than their American counterparts needed for the Norden. But the Luftwaffe 7 shared the Norden's fundamental limitations under combat conditions. It required clear visibility of the target, stable flight during the bombing run, and accurate input of flight parameters. When Luftwaffe bombers attempted precision raids against British targets in 1940 and 1941, their accuracy was no better than American bombers would later achieve with the Norden. The Luftwaffe 7's simplicity was an advantage in maintenance and logistics, but could not overcome the inherent difficulties of precision bombing against defended targets. Captured Luftwaffe 7 devices examined by Allied technical intelligence teams were assessed as competent designs well suited to their intended role, but inferior to the Norden for high-altitude operations. This assessment validated American development priorities, while confirming that German engineers had made rational choices given their operational requirements. After the war, approximately 1,000 unused Luftwaffe 7 bomb sites were found in Carl Zeiss factories and shipped to the Soviet Union. The Soviets attempted to install them in American-built B-25 Mitchell bombers that had been supplied under Lend-Lease and retained in Soviet service. The integration proved problematic, as the Luftwaffe 7 interacted poorly with Soviet-designed autopilot systems. The problems were never fully resolved, and the Soviet Air Force eventually abandoned the effort in favor of developing indigenous bombing systems. The strategic bombing campaigns of World War II, conducted by both the Western Allies and by Germany in its brief offensive phase, demonstrated that industrial warfare had become three-dimensional. Control of the air was not merely a supporting element for ground and naval forces, but a decisive strategic domain in itself. The side that could protect its own industrial base while destroying the enemy's production capacity could generate material superiority that would eventually overwhelm tactical skill and operational excellence. But achieving decisive strategic effects through bombing proved far more difficult than pre-war theorists had anticipated. Industrial targets were resilient, capable of dispersing production to smaller facilities or repairing damage faster than bombing could inflict it. Transportation networks, while vulnerable, were also resilient, with alternate routes and repair capabilities that limited the effects of localized destruction. Civilian populations, rather than breaking under aerial bombardment as theorists had predicted, often became more determined to resist. The entire strategic bombing enterprise succeeded only when applied with overwhelming force over sustained periods, exactly the opposite of the swift, economical, precision warfare that advocates had promised. The Norden Bombsight, examined in this context, was not a failure so much as a partial success that revealed the limits of technological solutions to strategic problems. The device worked as designed within its operational envelope. It provided unprecedented accuracy under favorable conditions. It enabled American bombardiers to attempt precision attacks that no other air force could match during daylight operations. But it could not overcome the fundamental challenges of bombing through weather and enemy defenses against resilient targets defended by determined opponents. The precision that seemed achievable in testing proved elusive in combat, not because the technology was flawed, but because combat introduced variables that no mechanical computer could fully account for. The psychological impact on American bomber crews of carrying the Norden deserves consideration. Bombardiers had sworn oaths to protect the device with their lives. They understood that it represented America's best hope for humane strategic warfare. The pressure to achieve results with this marvel of technology, under conditions of extreme stress and danger, was immense. When bombs missed their targets, when entire missions scattered ordnance across German countryside because clouds obscured aim points or fighters forced evasive action, bombardiers felt personal responsibility for failure. The gap between the pickle-barrel accuracy promised in training and the reality of combat performance created disillusionment that affected morale. Some crews reportedly took pleasure in jettisoning their Norden bombsights when forced to lighten aircraft during emergencies, a telling indicator of frustration with a device that had been sold as near miraculous, but performed only incrementally better than simpler alternatives under actual combat conditions. German engineers who examined captured Norden bombsights taken from downed American bombers in 1943 and 1944 confirmed the assessments made from Hermann Lang's 1938. Intelligence. The device was sophisticated, beautifully engineered, and precisely manufactured. It represented excellent application of available technology to a specific problem. But it was also complex to the point of fragility, difficult to maintain under field conditions, and optimized for a mission profile that German doctrine had rejected. The Germans found nothing in the captured devices that changed their earlier conclusion. The Norden was an American solution to an American problem. It did not solve problems the Luftwaffe actually faced. By the time these examinations occurred, the strategic initiative had passed entirely to the Allies. Germany was fighting a desperate defensive war, attempting to protect its cities and factories from round-the-clock bombing by the combined bomber offensive. The 8th Air Force raided by day with Norden-equipped B-17s and B-24s. RAF Bomber Command attacked by night, with simple vector bomb sites and area attack tactics. Together, they delivered over 2.7 million tons of bombs onto German-controlled territory between 1940 and 1945. The Luftwaffe, its strength bled white, defending against these raids and supporting increasingly desperate ground operations on collapsing fronts, had no spare capacity for strategic bombing, even had German commanders wished to pursue such operations. The post-war accounting of the strategic bombing campaign revealed costs that would have seemed incomprehensible to the optimistic pre-war theorists who had envisioned quick, economical, precision strikes deciding conflicts without massive ground battles. The United States 8th Air Force alone lost over 4,000 heavy bombers destroyed in combat, with thousands more damaged beyond repair or written off after emergency landings. Aircrew casualties exceeded 47,000, killed and missing, approximately 26,000 prisoners of war, and 18,000 wounded. These losses occurred despite the protective qualities of high altitude, heavy defensive armament, fighter escort, and all the technological advantages American industry could provide. RAF Bomber Command's losses were even heavier in proportion to sorties flown, with over 55,000 aircrew killed during the war, a casualty rate exceeding 70% of all personnel who served in bombers. The Allied air forces had achieved air supremacy over German-controlled territory by mid-1944, enabling the Normandy invasion and supporting the ground campaigns that destroyed German field armies. But supremacy had been purchased through attrition that consumed aircraft and trained crews at rates that only American and British industrial capacity could sustain. Germany's decision not to pursue strategic bombing, examined from post-war perspective, appears to have been strategically sound given German resources and geopolitical position. The Luftwaffe's focus on tactical air support and air defense, while inadequate to prevent defeat, at least concentrated limited resources on missions that supported ground operations. Had Germany divided its aircraft production between tactical and strategic air forces, building heavy bombers instead of fighters, the result would likely have been weakened tactical capability without corresponding strategic gains. Germany simply lacked the industrial base to simultaneously maintain a tactical air force, a strategic bombing force, and sufficient fighters to defend its own airspace against Allied bombing. The prioritization reflected rational allocation of scarce resources to missions with highest military utility. The failure of German air doctrine lay not in rejecting strategic bombing, but in underestimating the importance of air defense and the scale of Allied air power that would eventually be deployed against German territory. Germany's industrial capacity and technological sophistication should have enabled production of sufficient fighters and anti-aircraft weapons to make the combined bomber offensive prohibitively costly. Instead, fighter production was delayed by dispersed development programs, and anti-aircraft artillery, while effective, could not be produced in quantities sufficient to protect all vital areas. The jet aircraft and advanced anti-aircraft missiles that might have transformed air defense reached operational status too late and in insufficient numbers to affect the war's outcome. The Norden Bombsight's legacy extended well beyond World War II, finding continued use in conflicts where its precision capabilities remained relevant. The United States Air Force retained the device through the Korean War, where improved accuracy from high-altitude B-29 striking bridges and industrial targets demonstrated that under less intense defensive conditions than faced over Germany, the Norden could achieve results closer to its design. Specifications. The last combat employment occurred in 1967, when the United States Navy's VO-67 squadron used Norden-equipped aircraft to drop acoustic sensors along the Ho Chi Minh Trail in Southeast Asia. By then, radar-based bombing systems and eventually precision-guided munitions were replacing mechanical bomb sights entirely, finally achieving the pinpoint accuracy that Carl Norden had pursued but never fully realized with purely mechanical means. The technological principles embodied in the Norden influenced post-war development of fire control systems, inertial navigation platforms, and analog computers for military applications. The gyroscopic stabilization techniques refined for the bombsight found applications in missile guidance systems, ship-mounted weapons directors, and aircraft autopilots. The mechanical computing methods, using gear trains and integrators to solve differential equations in real time, represented the state-of-the-art in analog computation and informed development of more sophisticated systems throughout the 1950s and 60s. When digital computers eventually replaced analog systems, engineers who had worked on devices like the Norden brought understanding of real-time control problems and stabilization techniques that shaped how digital systems were implemented. Carl Norden himself lived to see his bombsight become obsolete, though he did not witness its final combat use. He died in Zurich, Switzerland, in June 1965 at age 85, having spent his final years in the country where he had studied engineering 60 years earlier. His device had achieved fame, though not the precision he had promised. The claim that bombardiers could drop bombs into pickle barrels from 20,000 feet, attributed to Norden's own promotional efforts through his business partner Theodore Barth, had become both the bombsight's defining legend and its most obvious failure when measured against combat performance. Yet Norden had succeeded in creating the most advanced bombing instrument of his era, a device that pushed mechanical computation and gyroscopic stabilization to their practical limits. That these limits proved insufficient for the demands of combat did not diminish the engineering achievement. The security classification that had surrounded the Norden during the war was gradually relaxed in the post-war period, with the device being publicly displayed for the first time in November 1944, when the classification was downgraded. By then, hundreds of Norden-equipped bombers had been shot down over German territory, and Allied authorities knew Germany had thoroughly examined captured examples. The elaborate security procedures, the oaths sworn by bombardiers, the armed guards, and secure vaults, all had been rendered moot by combat attrition. The reality was that the Norden's secrets had been compromised from the beginning, known to Germany before America entered the war, and ultimately irrelevant to German operational needs. Hermann Lang served 12 years of his 18-year sentence, being released in 1950 and deported to Germany, where he lived quietly until his death. The Duquesne spy ring case, successfully prosecuted by the FBI, represented the largest espionage conviction in United States history and demonstrated that American counterintelligence capabilities had matured significantly since the First World War. But the practical impact of Lang's espionage on the war's outcome was minimal. He had provided Germany with information Germany chose not to use, a perfect example of how intelligence value depends not on the secrets obtained, but on whether those secrets address real operational needs. The American perspective on the Norden bombsight controversy shifted over subsequent decades as classified documents were released and military historians examined wartime records. Initial post-war assessments, influenced by the desire to justify strategic bombing and the enormous resources invested in the campaign, tended to emphasize successes and downplay the gap between promised and achieved accuracy. The United States Strategic Bombing Survey, despite noting significant limitations in bombing effectiveness, generally supported the conclusion that strategic bombing had been decisive. Later scholarship, drawing on German records and more critical analysis of bombing data, produced more nuanced assessments. By the 1970s and 80s, historians were noting that German war production had peaked in mid-1944, despite years of intensive bombing, suggesting that strategic bombing's effects had been overestimated. More recent analysis has attempted to distinguish between different phases and aspects of the bombing campaign. The early precision bombing attempts, using the Norden against specific factories and industrial targets, achieved limited success at high cost. The later shift to area bombing and attacks on transportation infrastructure proved more effective at disrupting German war production, not through direct destruction of factories, but by preventing raw materials from reaching production facilities and finished goods from reaching frontline forces. The oil campaign, targeting German synthetic fuel production in the war's final year, achieved dramatic results because Germany's fuel stocks were already depleted, and attacks on refineries were relatively easy to execute compared to targeting dispersed factories. The bomber offensive's greatest contribution may have been forcing Germany to divert enormous resources to air defense, including fighter aircraft that might have supported ground operations, anti-aircraft artillery that might have served as anti-tank weapons, and the labor of hundreds of thousands of personnel needed to man defensive systems. The Norden's role in this strategic effect was enabler rather than decisive factor. It provided American bombers with credible precision capability that forced Germany to defend point targets as well as area targets, complicating defensive planning and resource allocation. Without devices like the Norden, American bombers might have been forced to adopt night operations exclusively, allowing Germany to concentrate defenses differently. But the Norden did not deliver the transformation in warfare that its advocates had promised. The ability to surgically destroy an enemy's capacity to fight while leaving civilian infrastructure intact. The comparison between American and German bombing doctrine, examined through the lens of Bombsight technology, reveals how tactical tools shape and are shaped by strategic choices. America chose precision bombing doctrine first, then developed the technological means to attempt it, investing heavily in both the Norden bombsight and the heavy bombers to carry it. Germany chose tactical air support doctrine and developed simpler bombing technology adequate for that mission. Neither choice proved optimal for the war that actually unfolded. American precision bombing achieved far less precision than doctrine promised, but evolved into an effective, if blunt, instrument for destroying German industrial capacity. German tactical air support worked brilliantly in the war's early campaigns, but proved inadequate when Germany faced strategic bombing of its own territory and needed long-range strike capability against Soviet and Allied industrial centers. The historical irony is that both nations developed competent bombing technology that worked reasonably well within its design parameters, but neither nation's doctrine fully anticipated the nature of industrial warfare in 3 dimensions. The Germans who examined the Norden in 1938 saw an overcomplicated device optimized for a mission profile they had rejected. They were correct in their assessment, but wrong in their implicit assumption that their chosen doctrine would prove sufficient. The Americans who developed the Norden saw a technological solution to the precision bombing problem. They were correct that technology was necessary, but wrong in assuming technology alone could overcome the challenges of combat conditions and target resilience. Both nations learned through costly experience that strategic bombing required not precision but overwhelming force, not technological elegance, but industrial capacity to build bombers faster than the enemy could destroy them. The engineering achievement represented by the Norden should not be diminished by its operational limitations. The device pushed mechanical computation to levels that would not be matched by analog computers until electronic systems became available in the post-war period. Its gyroscopic stabilization provided performance that informed development of inertial navigation systems used in missiles and spacecraft. Its integration of multiple functions, sensing, computing, and control, within a single system, anticipated the integrated avionics that would become standard in later aircraft. That it could not deliver pickle-barrel accuracy under combat conditions reflected not engineering failure, but the impossibility of achieving such precision with mechanical systems operating under the stresses of combat. The Norden worked as well as any mechanical bombsight could have worked, given the technology available in the 1930s and 40s. Its limitations were the limitations of the technology itself, not of its implementation. The human cost of strategic bombing, borne by both aircrews and by civilians in targeted areas, provides sobering context for any discussion of bombing technology and doctrine. Over 100,000 Allied airmen died in strategic bombing operations over Europe. German civilian deaths from bombing exceeded 300,000, with millions more left homeless by the destruction of urban housing. These casualties resulted from a form of warfare that pre-war theorists had believed would be more humane than the trench warfare of the First World War. The reality proved otherwise. Strategic bombing killed massively, destroyed indiscriminately despite precision bombing intentions, and traumatized entire populations. It achieved strategic effects only when applied at scales that made precision irrelevant and humanity impossible to maintain. The Norden bombsight, designed by a man who believed accurate bombing would reduce suffering in war, instead became part of a strategic bombing apparatus that killed and destroyed on unprecedented scales. The fact that Axis powers practiced their own forms of strategic terror, from the Blitz against British cities to the V-weapon campaigns, does not diminish the moral complexity of Allied strategic bombing. The attempt to maintain ethical distinctions through precision bombing deserves recognition, even though the attempt largely failed under combat conditions. The technical story of the Norden bombsight, from its development through its combat employment to its eventual obsolescence, reflects broader patterns in military technology development. Sophisticated weapons designed for specific doctrines often perform poorly when doctrine meets reality. Technology developed under peacetime conditions faces challenges in combat environments that testing cannot replicate. The relationship between technical capability and operational effectiveness is mediated by training, logistics, maintenance infrastructure, and the enemy's countermeasures. The most advanced weapon is not necessarily the most effective weapon if it cannot be maintained, operated reliably, or employed in ways that survive enemy opposition. The Norden's complexity, its greatest technical achievement, proved to be an operational liability under field conditions. Simpler systems, while less capable in theory, often outperformed more sophisticated equipment in practice because they were more robust, easier to maintain, and more forgiving of operator error or damage. The legacy of the Norden in popular culture has been shaped as much by the mythology surrounding it as by its actual performance. The image of bombardiers peering through the Norden's eyepiece, making minute adjustments as they guided tons of high explosive toward targets far below, has become iconic in depictions of World War II air warfare. Movies and documentaries have reinforced the notion of the Norden as America's secret weapon, the technological edge that enabled victory through precision bombing. This mythology serves narrative purposes, providing a tangible symbol of American technological prowess and ethical superiority in warfare. The reality that the Norden worked imperfectly and that American bombing often resembled British area tactics more than the precision doctrine promised, complicates these narratives but also makes the historical record more honest. The American bomber crews, who flew through flak and fighters, trying to aim the Norden under impossible conditions, deserve recognition for attempting precision even when conditions made it unachievable. Their courage and sacrifice should not be diminished by acknowledging that the technology they relied upon could not deliver what had been promised. The contrast between American and German approaches to bombing technology crystallized in those moments when German engineers examined captured Norden bombsights and confirmed their earlier assessments. Here was physical proof of America's precision bombing technology, the device around which entire strategic doctrine had been built, and German technical evaluation concluded it offered nothing Germany needed. This disconnect between American prioritization and German dismissal reflects fundamentally different theories of air power and different strategic circumstances. Neither theory proved wholly correct. The precision that America sought remained elusive throughout the war. The tactical focus that Germany pursued left them vulnerable to strategic bombing they could not counter effectively. The truth emerged only through combat, where both doctrines were tested and found wanting in different ways. The story that began with Hermann Lang sketching bombsight components from memory in Colonel Ritter's Hamburg office concluded with American strategic bombing, reducing German cities to rubble despite German knowledge of American bombing technology. The espionage had been real, the intelligence had been valuable in theory, but the practical impact had been nil because Germany had already chosen a different path. By the time German engineers understood through bitter experience that strategic bombing could be decisive when applied with overwhelming force, it was far too late to build the four-engine bombers and sophisticated bombsights that might have enabled Germany to conduct similar campaigns against Soviet or Allied industrial centers. The window for such strategic choices had closed years earlier, when Germany committed to tactical air doctrine optimized for continental warfare in support of ground forces. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.